So the workhorse, okay, the main machinery that is in operation to get posterior is what we call MCMC, Markov chain Monte Carlo. Markov chain Monte Carlo. And this looks like a pretty esoteric term here, right? Kind of mythical, right? So let me do a bit of, word analysis of this term. The first is, the first part of these, this 4-word term, Markov chain. What is Markov chain? Markov chain basically is the process of sampling a new value from the posterior distribution. So sampling, okay, a new value from the posterior distribution, given or depending on the previous value, only preceding value or previous value, okay? So what is Monte Carlo? Monte Carlo is a term denoting the random simulation process, okay? Random simulation process. Before I get into technicality of MCMC, I'd like to go through the timeline of the development of MCMC. Andrea Markov, a great Russian mathematician, introduced Markov chains in 1906. And Stanislaw Yun, while playing card games and trying to come up with a basic MCMC method, that's called inversion method, in 1946. Okay, John von Neumann, while working on this neutron diffusion, that is thermonuclear and fission problems in 1947, and Nicholas Metropolis from 1947 to 1949, co-introduced Monte Carlo while working on the first computer that is called ENIAC, and the second computer, Enigma. In a piece to commemorate Stanislaw Yun, Nicholas Metropolis, 1987, in the paper, a collection of articles to commemorate Stanislaw Yun, indicated that probably Enrico Fermi, Italian-American, physicist, also Nobel laureate in physics, independently discovered the Monte Carlo method in 1930s. So just a side note. And then Metropolis and others introduced MCMC, that is Metropolis algorithm, in 1953. And let's continue. The Metropolis algorithm was generalized to the Metropolis-Hastings algorithm by W. Hastings in 1970. Okay. Hastings only wrote 3 papers in his lifetime, and one of them is this watershed seminal paper on Metropolis-Hastings algorithm. So a legendary figure. Then Gibbs sampler and Gibbs sampling was introduced to statistics in 1984 by Gaman and Gaman. Okay, the BUCS, which stands for Bayesian inference using Gibbs sampling project, that is to implement MCMC methods using computer software, began at Cambridge, United Kingdom, in 1989. Gelfand and Smith, 1990 paper, believed to be the genuine starting point for intensive use for MCMC methods by the mainstream statistical community. So this is not long time ago in terms of large scale mainstream implementation of MCMC and application of Bayesian methods in the statistics community and related fields. Okay. So what is Markov chain? Here again, I will not get into very technical part of Markov chain. Here, what I'm trying to do is to give you a layperson description of what Markov chain is, how it was derived, and the general application. So a Markov chain is a stochastic process. It is named after, as discussed in one of the previous slides by Andreevich Markov. Sometimes it's spelled as Markov, Markoff, who is a great Russian mathematician. Markov belonged to the St. Petersburg Mathematical School founded by Chebyshev. Okay? And basically, the idea of Markov chain states that the probabilities of current event outcomes only depend on the outcome of the immediately previous state. So there could be a long chain of events, one after another. Markov chain argues that the probability, or what Markov chain describes is a process in which the probabilities of current event outcomes only depend on the outcome of the immediately previous state. So for example, there could be 3 states for weather, let's say sunny, cloudy, and rainy, right? And there's also probability, for having a rainy day, for having a sunny day, and for having a cloudy day, right? Basically, it says the probability of having a rainy day only depends on the state of yesterday, not the day before yesterday. Okay, so because yesterday, theoretically speaking, there can have 3 weather states too. So theoretically speaking, yesterday also has or had 3 states, possibly, right, of weather. One is, let's say a sunny day, a rainy day, and a cloudy day, right? What Markov chain describes, characterizes a process is that, today's, that's a probability of one of the 3 states, okay, depends on the outcome of yesterday. So let's say, here I'm just to come up with a example. Let's say, yesterday was a rainy day. Then the probability of having a second rainy day gonna be, let's say, 0.3. A sunny day will be 0.5, and cloudy day will be 0.2. And that outcome that set of outcomes only depends on the outcome of yesterday. Let's say yesterday was a sunny day. Then let's say today's probability of having a rainy day, let's say, is 0.6. Okay, a sunny day again is 0.2. A cloudy day is 0.2. See, depending on the status of yesterday, the weather state of yesterday, okay, the probability of having sunny, rainy, and cloudy day also varies. So that's the main idea of Markov chain. So the probabilities of current event outcomes only depend on the outcome of the immediately previous state. And also in response to his colleagues, here is Nekrasov's assertion that the weak law of large numbers only pertains to independent events. Markov proved that independence is not a necessary condition for the law tell, in this case, Markov chain, right? You know, there is a dependence going on, right? Today's or the outcome, okay, for the current experiment, you know, we can call that experiment, right? The probability of the outcomes of current experiment only depend on the outcome of the immediately previous experiment. Yeah?